one.
Yeah, I can
Everybody
see.
can
you
see
also
what I'm presenting?
I can see it. Can you also see the Q&A box?
Yes, I've got it.
Okay.
Okay. So yes, as Ken said, we're going to be talking about Mars 2020 today. Launched about 7 months ago, July 30th of last year. In the middle of the pandemic, it was incredible that we're able to still get the spacecraft down to the Cape, onto the launch vehicle, and on its way. Because for those who were at my previous lecture, we're only able to go to Mars with traditional chemical rockets about 1 month every 26 months. That's when the window opens where the energies are in the range that our launch vehicles can actually get a spacecraft out to Mars. So that first lecture, we were talking about the mission. I will do a recap of what 2020 is. So for those who weren't there, we'll kind of understand what 2020 is, what its mission is, what it's trying to do. And then the rest of the second part of this is going to be more of a deep dive into the entry, descent, and landing phase of the mission. Some may remember from the Mars Curiosity mission, the 7 minutes of terror video that made its way around social media. We're going to be doing essentially the exact same concept with a few minor tweaks that have some advantages and enable this rover particularly to go to a much more hazardous landing site than what Curiosity was able to do. And that's because of some of the updates in the technologies, some of the systems that we have on board allowed the scientists to be able to choose a much more scientifically rich environment with some more hazards in the landing area. But with these new technologies, we're able to actually safely get the vehicle to the ground. And that's what most of the analysis is showing us. So 2020 is marketed as NASA's first leg of a Mars sample return mission. So Perseverance's mission truly is the beginnings of the search for ancient microbial life on Mars. And we're going to a very special place on Mars where we think we have the best chance of finding that life if it was once there in Mars's ancient past. So as Ken said, I'm formerly from JPL, was hired in as a flight controller for the Cassini mission right out of graduate school. Flew Cassini around Saturn for about 20 months or so until the spacecraft met its fiery end in the upper atmosphere of Saturn. In that time, I'd spent a short little stint working on the Mars 2020 mission systems development. So the actual ground software and the planning software that we use to actually drive the rovers each and every day. At that time, I was dual-hatted with the MER Opportunity rover. I was a systems engineer and a flight director for Opportunity, and was with that mission until Opportunity met its demise in a global spanning dust storm in 2018. And then before I left JPL, I was with a mission called NISAR. That's the next Earth Sciences Planet flagship mission. So it's a joint mission between NASA and the Indian Space Agency, ISRO, that's going to launch sometime, I think it's no earlier than May of next year. And then I got a call from someone out here in Dulles, Virginia, who was looking for a fall protection engineer to work for lunar missions on the Lunar Lander and Lunar Gateway. And because working on Mars isn't exciting enough, my wife and I thought, oh, why don't we come out to Dulles, Virginia, where it is currently 29 degrees Fahrenheit and it is sleeting and snowing, and will do for the rest of the day. I don't miss Southern California at all. And we now are working on the Gateway program, so getting astronauts out to permanent lunar presence around the moon sometime in 2024, probably might be 2025 now, depends on what the new budget is. And because I'm not busy enough, I'm also in in the military as a reserve officer, so I keep myself very busy. So disclaimer up front, we just have to do this just to make sure that everything I talk about here is my opinions. This is all from publicly available information. I will give you all the links to the sites where all the information is. I will say that JPL does a really good job of explaining these missions in such a way that you, the audience, can really become immersed in the engineering, the science, the mission, and everything related to it, so that you can feel like you're kind of along for the journey. So let's talk about the mission overview. So the Perseverance rover will search for signs of life in Jezreel Crater. And the reason we're going to Jezreel Crater is from orbit, actually a graduate student who was interning at JPL was looking at high-rise images from the Mars Reconnaissance Orbiter and was able to deduce from the orbital images from the spacecraft that Jezreel Crater is an ancient river delta. An ancient river delta being a place where water was flowing upstream and then deposited minerals into this river delta, into this crater basin. Well, Mars's climate is very different than what it was in the past, so all the water is gone. The geological evidence is all still there. It's in the rocks. And that is where the scientists wanted to go when 2020 was first proposed, and then eventually became the first leg of a Mars sample return mission. If we think life was once on Mars in its ancient past, and we're talking about microbes here, we're talking about bacteria, nothing too complex. But if it did once exist on Mars, we think that this river delta is a great place to go look. The rover has 7 different instruments that it can use to sort of interrogate the area around Jezreel Crater. It can look into the geological past to determine the climate, the area's suitability for hosting life. And if we think that this place that we're looking at has all the signs that we're looking for, the rover has a very special instrument on board called the sample caching system. And what it can do is it can use a drill on the end of its arm that can core sample into the soil, and then it transfers that sample into the interior of the rover, and from there the sample is capped, it is hermetically sealed, and it is stored for eventual pickup by the Mars sample return mission, which is now under study by JPL and the European Space Agency, for eventual pickup and return of those samples to Earth. The instruments on 2020, and we get this question a lot, the instruments on 2020 are sufficient enough to interrogate the past habitability of the site, but they're not good enough to tell whether there was actual life there. To really make a definitive conclusion, we have to bring those samples back to the laboratories here on Earth that have the instruments with the capabilities to actually detect those things. The other really neat feature of this mission is that we can test technologies for human exploration. We actually have a very special instrument on board, Moxie here, and I'll play this video here in a second, that actually is going to demonstrate turning Martian carbon dioxide into oxygen. So for those who are fans of The Martian and have read the book like myself, this is equivalent to the oxygen reclaimer that Mark Watney used in order to turn Mars's atmosphere into breathable oxygen, as well as rocket fuel for the Mars Ascent vehicle that they used. Now, the prime mission, and this is very important. So the rover is designed to last for a single year on Mars. That's about 687 Earth days. Now, the rovers typically are really good. We take really good care of them, that they can last much longer than their prime mission. Curiosity, for instance, is going into its 9th year on the surface of Mars. It too only had a mission, a prime mission of 1 year on the surface, but it is the RTG that it uses is still outputting sufficient power, and they're able to still do good science. So Curiosity is still churning its way on the surface of Mars even today. We probably expect that Perseverance will also be around for much longer, but for the initial funding, Perseverance is only funded for a single Mars year on the surface. And within that Mars year, they have to do a lot of science. They got to get their samples cached, and they got to get them deposited on the surface. And then if they still have samples left over, they still have consumables left on board, and they still have science they can do, then they'll propose and go after a second mission. So I'm going to play a video here for us. This is going to give us an overview from JPL on the mission itself. Ken, if you can't hear the video, please let me know, and I will exit out of here and reset everything. Okay.
Okay.
Mars is the closest place that we can reach with robotic exploration that we think had a really good chance of having ancient life.
The Perseverance rover will land at a location called Jezreel Crater. Jezreel Crater is a very interesting place. It's a crater that once held a lake.
There are a lot of craters on the surface of Mars that could have once hosted ancient lakes, but not every crater that we think had a lake actually preserves evidence that that lake was there.
It had an inflow channel and it had an outflow channel. That means it was filled. The crater was filled with water.
In Jezreel, we have probably one of the most beautifully preserved delta deposits on Mars in that crater.
This is a wonderful place to live for microorganisms, and it is also a wonderful place for those microorganisms to be preserved so that we can find them now so many billions of years later.
There is no other place on Mars that has the unique combination of a lake setting, a beautifully preserved delta, and the diverse mineralogy that we have in Jezreel Crater. So it's truly a special landing site.
The major goal of the Perseverance mission is to investigate astrobiology on Mars, and in particular, to address the question of whether life ever existed on Mars. The Perseverance rover starts with a design that's very similar to Curiosity, but we've added to it a whole new set of science instruments. And these science instruments were purposefully selected to help us in the search for biosignatures.
We're going to be taking microphones with us. For the first time, we're going to have that human sense on another planet.
Perseverance carries with her a grand experiment in spacefaring technology, a helicopter, the name of which is now Ingenuity.
One of the major upgrades that Perseverance has from Curiosity is that it's able to self-drive for a distance of up to 200 meters per day. As the rover is driving, it's literally building the map of the road it's driving on Mars.
Scientists for years have told us that to really unlock the secrets of Mars, we have to bring samples from Mars back to Earth.
So what Mars 2020 is going to do is to drill samples, put them in small tubes. We're going to seal it in its own individual tube. We set them on the surface to provide a target for the second two missions, which hopefully will get in development in the next several years and could potentially get the samples back to Earth by 2031.
Perseverance is a very, very profound first step in both our understanding of our place in the universe and a stepping stone towards human exploration on Mars.
Okay. So as many of the science team members, you saw on there, Dr. Katie Stack-Morgan, she's the deputy project scientist, awesome human being. I can't say enough about my colleagues, my former colleagues at JPL. They're all just really great people. And if they're going to find life on Mars or past preserved ancient life in the rock samples, this team is very well suited and capable of doing that. So as stated, the science objectives for Perseverance, the big one is the search for signs of habitability and biosignatures. So this is truly NASA's first what we call an astrobiology mission. It's actually has the instruments on board to be able to look for signs of past habitability and biosignatures. So what a lot of the other rovers prior to Perseverance have done is search for signs of habitability. So they look at the climate, they look at, we can look at what the atmosphere, the humidity, the pressures, the temperatures, we can see that in the rocks. And we have the instruments on board that can actually look for that. And then the passive biosignatures is there are some instruments on board that even have the capabilities to detect traces of organic compounds within the rocks. So that's able to tell us, whether or not there was some organic processes going on within the rocks. And that will help determine which core samples we need to take. The third piece of this is actually core sampling. So most of the instruments on board are meant to perform the sample caching mission. So they determine which samples within the Jezreel Crater site meet all the requirements for sample caching, and then the sample caching itself is a series of three separate elements, three pieces of hardware that actually are able to drill the core sample, transfer it into the rover, contain it, and then seal it on board for eventual placement on the surface. And then that last piece is preparing for humans, so testing oxygen production from the Martian atmosphere. It's pretty neat that a mission of this size, especially with such an important science question to answer, was able to get an engineering technology demonstration instrument on board with Moxie, which we'll talk about the instruments in a second. But personally, for an engineer, I think it's really neat to have an instrument going on a Mars rover that is simply for an engineering technology demonstration. Because engineers, we typically don't get to really play around with proposing instruments for missions like this. It's all the science team. So I think that's a really neat piece of this mission that's going to really pave ways for future human exploration on the surface. So for the spacecraft overview, we always talk about Perseverance is just the rover. So Mars 2020 is an entire integrated spacecraft system. The thing that actually gets deposited on the surface, the rover, is the one that everyone cares about, but there's multiple elements to the spacecraft system that actually get it to the surface. So what is composed here is what is currently cruising on its way out to Mars. That piece at the very top, that is called the cruise stage, and it's essentially it's its own little spacecraft. So it has solar panels on board that provide power to the whole spacecraft stack, as well as charge the batteries on the rover. The rover is the only piece that actually has batteries on board. It has everything you need, including telecom systems. It has a low gain and a high gain antenna. That's how we communicate back and forth with the spacecraft as it cruises out to Mars with Earth. It's got, like I said, it's got solar panels. It's got a propulsion system for doing trajectory correction maneuvers. It's got star trackers. It's got sun sensors for figuring out where the spacecraft is. Those white panels on the side, those are the radiators. So that's how we do heat rejection from inside of the spacecraft. So we make sure that we don't, get the rover too hot or too cold. The back shell there, that next piece that looks kind of like a cone, that is one of two pieces of the Aeroshell, which is the piece that enters the Martian atmosphere. It's got its own set of thrusters to help us with the guided reentry part of entry. It's got some ballast weights in there, and the other important thing it has there is the parachute. That's where we keep the supersonic parachute. When we get to the EDL section, we're going to talk about why we need a parachute. But connected next to that is what we call the descent stage, also the sky crane. That's basically our rocket backpack. That is mechanically attached to the rover, and that's what does the last powered descent portion of EDL before the rover actually touches down. And then that piece at the very bottom there, that is a heat shield that's slightly upgraded from Perseverance. Not from Perseverance, from Curiosity. It's really hard to keep the names of the rovers together sometimes. But that heat shield, just your standard heat shield you need for any type of atmosphere planetary reentry. The neat part of that is, from an engineering perspective, we have lots of sensors wired up on the inside of the heat shield, so we can actually take measurements of the reentry field. That just helps us upgrade for when we do other entry descent landings. We have a little bit more data on how the performance of the heat shield were, what the temperatures were on the outside, what the pressures were, and that just kind of helps us update our models for future missions. So the rover itself is its own little spacecraft. It has everything that you would expect a spacecraft needs to perform. So we have computers with intercommunication links, both prime and redundant. Spacecraft of this size doing this kind of mission, there is redundancy on everything. So I'm kind of speaking here as a fault protection engineer. We have at least single fault tolerance on pretty much everything. So you have 2 computers, you have 2 telecom boxes, you have redundant sets of heaters, you have not redundant instruments, but you have redundant power interfaces and redundant batteries and all these things. We put the redundancy in there to make sure that we can actually meet that one year mission goal. For power, same thing as what Curiosity had. We have what's called a multi-mission radioisotope thermoelectric generator, an MMRTG. We basically take non-weapons grade plutonium that is provided to us by the Department of Energy. You put it inside of a box. You take 2 wires of dissimilar material, and you create basically a thermocouple. And the difference in the temperature between the inside of the box, which is very hot, and the outside of the box, which is very cold, is what generates the current that we then use to supply power to the vehicle. At launch, we get about 110 watts, and because it is radioactive, it does decay. So the amount of power that the RTG is able to supply to the rover does decrease by a few percentage points over the years. Curiosity, I'm not exactly sure where Curiosity's power is at, but to give you a perspective, the Voyager spacecraft launched in 1977 with an RTG, and they are both still able to communicate with Earth while doing some limited science, not the full breadth of science they were able to do on their prime missions, but they still have sufficient power to keep operating 40 plus years later. So RTGs are very reliable. The great thing about an RTG is if you're someone like me who worked on a solar powered rover, you don't have to worry about dust destroying your only energy source, which is the sun. Curiosity was able to operate perfectly fine through the dust storm in 2018, whereas Opportunity died a very slow death because it was starved of any solar power it needed to charge its batteries. So big advantage, and that's how one of the ways we're able to actually guarantee that we can survive on the surface of Mars for a year is because we have an RTG. For telecom, on the surface, we have X-band, which is what we use to do direct to Earth, what we call DTE communications with the DSN. That's how we get the command uplinks into the spacecraft every day. And the majority of the spacecraft data, including all the science data, goes through a UHF link, and we use the orbiters in Mars orbit as part of a Mars relay network that we use to relay our data from the surface to the orbiters, and we use what's called a bent pipe method. And that's how we get the data from the surface of Mars back to Earth. For the majority of the data, because of how much we're generating, we use the orbiters instead because they have the bigger telecom packages, they have the bigger dishes, so they can do much higher data rate returns back to Earth than what the rover can do from the surface. And then, of course, we have thermal protections, so both passive and power switching heater elements that are able to supply power. Mars gets very cold, actually. In the winters, we can get down to over minus 100 degrees centigrade, and sometimes as high as a balmy 25 degrees centigrade in the summer. So there are thermal cycles on the vehicle, so we do have to have passive thermal protection as well as the heater elements. Some things that are unique to rover surface missions. One is the mobility system. So not the rocket bogie, that's actually supposed to be the rocker bogie. That was a technology demonstrator that was sent with the Mars Pathfinder mission in 1997 to demonstrate planetary mobility systems. And it is the same type of mobility system that we use on rovers today. So it's a very reliable system. It works very well, and it allows us to basically drive over uneven terrains that we really can't see underneath us, and it works very well. So we've got a head and neck. So we have a camera mast that gives us human scale viewpoints. So when we have engineering cameras on the head of the rover, and that's what allows us to see what the rover sees from a human perspective. So that helps us generate our drive maps. That's how we're able to determine where we're going to drive to and how we also can avoid obstacles. This rover particularly is very smart in terms of Curiosity's it has the ability to do what we call auto navigation. So we basically can tell the rover where we want it to go. And the rover has a lot of built-in autonomy on board that it can use the images in front of itself, and it can create its own driving mesh on board. And rather than the engineers on the ground telling the rover where to, how to get to the location, we just tell it where to go, and it figures out how to get there. And the last piece is that arm in the hand. So that's how we're able to actually physically do contact science, touch the rocks that we want to actually observe, and then also how we're able to sample cache, how we're able to drill into the rock, get the core sample, and then transfer it back into the rover. For the instruments, like I said, we have 7 different instruments on board. So Perseverance is essentially, in an engineering term, we like to call it a build-to-print vehicle. It is Curiosity-like, but there are different instruments on board, and the vehicle was slightly modified in a way to meet the internal volume for the instruments, as well as to accommodate the different payloads and the power settings. So it is a build to print in terms of the chassis. Some of the boards are heritage, but the system mostly is a brand new system because it is operated differently, and its mission is very different than what Curiosity's mission was. So the Mastcan Z, this is a set of advanced cameras that have both panoramic and stereoscopic imaging with the ability to zoom. That's something that Curiosity did not have. So what they can do is they can basically use those cameras to determine the mineralogy of the Martian surface. And this assists with rover operations. So those are part of the cameras that we use in order to help us determine where we are, how to create our drive maps. And that's how the rover actually is able to determine its own autonomous drive map. So META is called the Mars Environmental Dynamics Analyzer, and this is basically our Martian weather post. So a series of different instruments can measure wind speed, can measure local barometric pressure, can measure humidity. It's basically like our own little weather station on Mars. MOXIE, this is the neat engineering demonstration experiment. So this is called the Mars Oxygen ISRU experiment, and it's an exploration technology that will produce oxygen from Martian atmospheric CO2. So that oxygen reclaimer we were talking about in the Martian, that is essentially the technology that MOXIE is going to demonstrate on the surface. PIXL stands for the Planetary Instrument for X-ray Lithochemistry. We're NASA, we have acronyms for everything. So this is an X-ray fluorescence spectrometer with a high resolution imager that's used to determine fine scale elemental compositions of Martian surface materials. So this is able to look at very, very fine scales and determine what the chemical makeup of the rock is. So that's how we're able to determine the past climate, the habitability elements of that area. So that's that first piece, which is the past habitability. The RIMFAX, this stands for the Radar Image for Mars's Subsurface Experiments. This is essentially a ground penetrating radar with centimeter scale resolution. So we can actually see down into the river delta. We can see at centimeter scale resolution, we can see the sort of 2-dimensional scan of the river delta that's beneath us. And then Sherlock, we certainly love acronyms in NASA. So this is called the Scanning Habitable Environments with Raman and Luminescence for Organics and Chemicals. It's a mouthful. We just call it Sherlock. It has a calibration instrument on board called Holmes. So Sherlock and Holmes, yes. So this is a spectrometer with fine scale imaging that uses an ultraviolet laser to determine the mineralogy and detect organic compounds. So this is the piece that actually allows us to detect the presence of past biosignatures, the actual organic compounds that could indicate the presence of past microbial life. So typically with missions of this size, we will basically cross-strap instruments so that we can answer all the questions without using a single instrument. So we basically cross-reference all the information that the instruments are taking together, and that helps us sort of put together a full picture of what this environment, what this particular area we're studying looked like in the past, what its climate was like, what its past habitability may be, and whether it had all the pieces necessary to support past ancient life. And last but certainly not least is SuperCam. This is basically that laser. So if you look on the picture there, that big glass eye there on the front, that is essentially a laser, and that's what we use to basically burn off the outer oxidized layer of a rock, so we can see down into what the rock actually looked like before the oxidation occurred on the surface. So the last really neat element of Perseverance is what we call the sample caching system. So Perseverance will collect, for the first time, we've never actually done this with a mission on the surface of Mars, samples from Martian rocks and store them in sealed tubes on the surface. So this is how we're actually enabling the Mars sample return concept. So the sampling is done in 3 steps, and we actually have 3 separate basically pieces of hardware on the rover that enable the sample caching to occur. So the first piece of the sample caching is we have to first collect the samples. We then have to bring them into the rover, and on the inside of the rover, it has another mechanism that's able to take the sample, get it into a hermetically sealed tube, and then place it for storage on the vehicle. And then the last piece is, at some point within Perseverance's prime mission, that's the goal, they will find a spot within Jezreel Crater, and they will deposit these samples. And what's under study now is the Mars sample return mission will land within a short distance to those samples. It will then send a little rover out, go pick up those samples and bring them back to a lander, which will then load them inside of a rocket and take them up into Martian orbit. So Perseverance has a requirement. This is a level 1 science requirement that it has to cache at least 20 samples within its prime mission. It has, I believe, 40, I think it's 40 or 42 total tubes on board. So it can sample more than 20, but 20 is the minimum requirement it has to cache within its 2 years. And that is what the Mars sample return mission will go out and retrieve for bringing back to Earth. Because the system is so complex, I was actually reading about this last night to try to sort of familiarize myself again with it. It's really complicated, so I'm just going to let the engineers who designed it actually explain it, because they can do it so much better than I can.
In terms of robots that go into space, the sampling and caching system on the Mars 2020 mission is the most complicated, most sophisticated thing that we know how to build. This is the system that allows us to take core samples of rocky material on the surface of Mars, carefully seal them in very sterile, clean vessels for eventual return to Earth. We've been working on the sampling and caching system for 7 years, and that's because it's a tough job.
We're testing the equipment to make sure that it's going to work when we get to Mars. It has to function on its own. We have to think of all eventual possibilities and try them here first. And then if they don't work, change it now, because we can't make any changes later.
To drill into the rock on Mars, pull out intact core samples, seal them hermetically, and to be all done autonomously by a robot hanging off the end of a rover on the surface of Mars has been a challenge. We've got actually 3 robots necessary to do the sample and caching system. Our big robotic arm out on the front of the rover, that takes our drill, pushes it against the surface, and allows us to take core samples. Then we put that core sample in the bit carousel, the second robot that takes that from the robot arm and puts it down inside our adaptive caching system. This is the part of the sample and caching system inside the rover. We've got a little tiny robot, a special robot arm called the SHAW, the sample handling arm. It takes the samples out of the bit carousel and moves them through volume assessment, image taking, and eventually to sealing, and then replaces the cylinder containing the sample in a storage spot, all on its own in the matter of a few hours. We have designs on bringing them back in a decade. Mars has been at the fore of our consciousness about the questions of life. Could life exist in one of our nearest neighbors? I think we have a lot to learn, life or no life, about the evolution of our solar system, about our planet, by looking in depth at rocks brought back from Mars.
So the interesting part about the sample caching is it is very technically challenging to pull off. But I think what is more interesting is what we have to consider is the reverse planetary protection effects with bringing back samples from Mars. What we're always concerned about is forward planetary protection, which is making sure that we're not taking our germs from Earth and putting them on Mars. Because if we're trying to look for life, if we build our rovers in a not very clean environment and we go to Mars and then we take samples and we find that there's bacteria in there, it'd be very difficult to determine whether the bacteria was there on Mars or whether we took it with us. So the neat thing is going the reverse direction, which is when we take samples of Mars, how do we ensure that we don't bring any potential Mars bacteria into Earth's biosphere? It's a very, very interesting problem that several individuals at JPL have been working on for over a decade. So let's now move to what I think is one of the neatest parts of this mission, which is the Ingenuity Helicopter. So like we saw in the mission overview, Perseverance is carrying with it a very, very, very special technology demonstration mission called Ingenuity. It's a small autonomous rotorcraft that will demonstrate controlled powered flight on Mars, something we haven't really ever done before. So there have been studies proposed about doing powered flight on Mars, whether that's a fixed wing aircraft or a rotorcraft. There've been studies in the past, but we've never actually had the ability to attempt this. Well, now Perseverance is going to take a small little CubeSat with a counter-rotating blade, and they're going to attempt to demonstrate controlled powered flight on Mars. And this is a tech demonstration. So when people ask, how many flights does the helicopter have to do? Does it have to be successful? And the answer is no. The helicopter does not have to take off and land for this to be considered a success. It's simply a technology demonstration. Now, the teams, as we'll see in the video, the teams have demonstrated that they can do controlled flight in JPL's TVAC chamber in realistic Mars conditions. So we know that it is possible. It's just going to be really neat to see it happen. The helicopter has it has cameras on board, so we'll be able to, when it takes off, we'll be able to actually downlink the data to the rover and actually see the thing take off in flight. Being able to see the rover on the ground from the helicopter when it's up in the air, I think is going to be really, really neat. So they're only planned to have one flight within 30 sols. There are opportunities to do multiple flights if they're able to, if they are able to demonstrate one flight successfully. I do think that they will try to do others. The problem is the helicopter is sort of like a dog on a leash for the rover. So when the rover moves forward, as long as the helicopter is still attached to them, they have to fly the helicopter back towards Perseverance so that they can keep moving. So eventually the helicopter is going to become a nuisance to try and do the primary science objective. So they will do, their one flight, and if they have an opportunity to do maybe one or two more, they will do those. But eventually, after 30 sols, they're just going to leave. They're going to leave the helicopter behind, so they can go off and do their primary science mission, which is to cache samples. So let's take a look here at the video here on Ingenuity.
Sometimes you have to do something just to show that you can do it. When the Wright brothers flew for the first time, they flew an experimental aircraft. And in the same way, the Mars helicopter is designed to show that we can fly powered helicopter flight in the Martian atmosphere.
From day one, this was the unwavering dream of our team, to get our helicopter launched to Mars so that we can get that opportunity to do that very first rotorcraft flight test in the actual environment of Mars. It's extremely difficult to fly at Mars because the atmosphere is so thin. compared to Earth's at Mars is less than 1%. So the first and foremost challenge is to make a vehicle that's light enough to be lifted. And then the second is to generate lift. The rotor system has just been very fast. 2,000, 2,200, 2,400, 2,600. We're spinning between 2,000 and 3,000 revolutions per minute, and it takes a lot of energy. So it's that balance of a very light system, yet having enough energy that's needed to, spin the rotor so fast to lift, and on top of it, having to design in the autonomy.
It has to be fully autonomous from the time it takes off to the time it lands. What we do on the ground is we plan the flights, and so we determine from here where we want the helicopter to go.
Our experiment window is 30 Martian days. So we have planned up to 5 flights of incremental difficulty.
The very first flight, the main thing is we want to get the legs off the ground, and so we will basically go up about 3 meters, and we'll hover there, and then we'll come down again, and that will be the first, really major milestone.
Most of our flights will be at the 3 to 5 meter height. We will be going horizontally again at a few meters per second, probably go out, 50, 70 meters and come back. In successive flights, we'll probably push that further, try to go further. So our priority will be to get back engineering telemetry and not so much images, but I'm sure we'll return a few, because they'll always look cool.
At this point, we've tested all we can on Earth. We have mathematical models that shows how it'll fly at Mars, and we've tested it in the simulated environment that we can create on Earth. It really is time now to do the real flight tests at Mars.
Nothing is a given, but we have done everything we can in terms of a test program here on Earth. The vehicle's performing extremely well so far. It's been doing exactly the right thing, even right now when it's bolted onto the Perseverance rover. So there's a very good chance that we'll pull it off, yes. But it's still high risk, and none of us forget that you could have a glitch that, could mean end of mission, yes.
It's going to be exciting, reacting to any surprises we have. We can't wait. What's really most important is everything we're learning here is for the future rotorcraft systems that we want to introduce into space exploration.
Yeah, as an engineer, that is going to be a really exciting part of the mission because like they're talking about, it has to be a completely autonomous system. It's not something where you can joystick it from Earth because of the lifetime delays. So not only do you have the difficulty of trying to do demonstrated controlled flight in Mars's atmosphere, which only has an atmospheric pressure at the surface of 1% of sea level here on Earth, but also you have to do this completely autonomously. So it's a very difficult engineering problem, but I think it's going to pay off for them very, very well. At least we hope it does. I hope they definitely get a shot at doing at least 1 or 2 flight demonstrations. Okay, so let's go to launch. So like I said, back in July 30th of last year, Perseverance took off at, was fine for me, 7:50 a.m., but 4:50 a.m., so very early in the morning out there on the West Coast. Up on an Atlas V, 5:41. Let's play this guy here real quick.
Status check. Go Atlas. Go Centaur.
Atlas
go
5.
Mars 2020.
5:41.
There we go. We are ready to go liftoff this morning, Joshua.
Liftoff went
8, 7, 6, 5, 4. Engine ignition. 2, 1, 0. Release and liftoff. As the countdown to Mars continues, the perseverance of humanity launching the next generation of robotic explorers to the Red Planet.
Yeah, liftoff was right on time. There were some delays in processing that, for those of us who have worked interplanetary missions before, that got us our blood pressure up a little bit. There were some issues with processing of the Centaur. There were issues with processing of the Atlas V, and then there were problems with ground testing, but they got the vehicle off on July 30th at the very opening of the window. You saw there, for those of us who do
status check. Go Atlas.
For those of us who do look at interplanetary flights, our Earth departure C3 velocity was 14.5 kilometers squared per second squared. So that is if you take the square root of that, we needed roughly a little more than 7 kilometers per second of extra delta V beyond Earth escape velocity to get us onto the correct interplanetary trajectory in order to intercept with Mars on February 18th. So now we take off, and we're basically in cruise. And is crew just, we just sitting back, relaxing, and just enjoying our flight for the next 7 months? No, we're pretty busy. We're actually doing a lot of stuff in the process of getting out to Mars. So you can see on the diagram here, we have listings of what we call trajectory correction maneuvers. So we have planned places within the cruise flight to correct our trajectory on the way out to Mars. Our major activities, we're doing spacecraft health and maintenance checks. We're doing checkouts and calibrations of the spacecraft systems and instruments. So we basically just look and see to make sure that the launch environment didn't hurt our systems at all, that everything still looks good. Everything is vibration tested in a realistic launch environment. So we know that the system and the hardware is able to survive that launch environment. We just do those checkouts just to make sure that's just engineers doing their due diligence. The big thing while we're flying out there is lots of radiometric navigation. We have to know where we are so that when we do our trajectory correction maneuvers, we actually make sure that we have a good understanding of where the spacecraft is going to be, so that when we fire the engines, afterwards we know that we're not adding too much dispersion into the flight, so that we can actually hit Mars's atmosphere. And when you get to EDL, you have to hit a very, very, very small window in Mars's upper atmosphere at the right time, or else EDL doesn't work. You basically either would skip off the top of the atmosphere and you wouldn't go into the atmosphere, or you would miss the planet's atmosphere entirely. Like I said, those TCMs, so on the diagram here, TCM 1, 2, and 3 is planned. Those are deterministic. TCM 1 is the biggest one that we perform in the entire flight. That takes out all of the extra launch dispersion errors that we induce. So when we fly to Mars, we actually point the spacecraft away from Mars. We bias it away from Mars. And that's because the Centaur upper stage is not clean enough to actually touch Mars's atmosphere. That is a planetary protection requirement, is that the upper stage of the spacecraft cannot actually impact Mars. And it's looking at probability. So it's like within the next 100 years, the upper stage will not impact Mars. So TCM1 is what we use to take all of that bias out of the initial trajectory. That gets us back onto the correct intercept point we need to make it for Mars. And if I recall right, Tori Bruno stated on Twitter that the 2020 launch, the injection accuracy was basically right down the middle. So we didn't have a lot of extra dispersions. That's great for us. It just means we have extra margin in our propellant when we get to the red planet. The last big thing, which the team has been doing quite a lot for the last couple of weeks, is EDL prep. So they've been doing the last checkouts of the EDL system, getting the thing ready to go for when we actually get to the red planet on Thursday for the EDL activity. So I'll just go through this real quick. Just a little crash course in how we actually get to another planet. So interplanetary flight is all about getting to your destination. So when we're flying through interplanetary space, we have lots of sources of error in spaceflight. So a big one is the injection errors from the launch vehicle. If your launch vehicle doesn't get you on the right trajectory, you pretty much don't have enough delta V in your spacecraft to fix it. So having a really, really, really precise injection from your upper stage is very important. But other things that are always pushing on us: solar and radiation pressure, gravitational perturbations. There's many, many, many others. So we're always getting errors induced into the spacecraft. So we use guidance, which guidance is what we call a reference trajectory. That is basically our transfer out to Mars that we design ahead of time, that our mission planners design. Navigation is we use orbit determination in order to determine where the spacecraft is, and then we use trajectory correction maneuvers in order to move the spacecraft back onto that reference trajectory that we want. So with orbit determination, so we have to know very, very precisely where the spacecraft is, both in terms of position and its velocity, relative to inertial frame. And we typically use the J2000 inertial frame as sort of a reference point. So the way that we do this is we use something called orbit determination, which is essentially a statistical technique that fits a least squares regression model against our reference trajectory using a ranging and velocity measure. So what we call it is range and range rate. I actually took a course on this at Georgia Tech. It was one of the most fascinating courses I took because I actually didn't know this is actually how you navigate. Our navigators at JPL are pretty much the best in the world at this. They pretty much invented the technique on how to do interplanetary navigation. So it's a very, very, very good technique. And using the Deep Space Network that we primarily use for interplanetary flight, we can get very, very, very accurate measurements of where the spacecraft is within sub-meters and sub-millimeters per second in terms of velocity. So the way that we get this information is we use a technique called radiometric navigation. So a dish on the ground basically sends out a ranging tone from a tracking station. You can think of it just like on a, it's just a tone. Hit an F natural on a keyboard. That's a tone. And that's what we send it to the spacecraft. The spacecraft's telecom system recognizes that tone as a ranging tone. It basically accepts it, and then it sends it right back down to the ground. So what we do is the time that it takes between when that signal is sent to when it is received is what we call the round trip light time. We basically divide by 2, multiply times the speed of light, account for any other errors, and we've got the one-way range and distance to the spacecraft from the ground station. And then for velocity, we use Doppler shift in order to determine what the velocity is. So basically the frequency delta between a two-way coherent signal. A coherent signal is when we get a coherent signal into the spacecraft. So that's when we have an uplink from the ground with a very known stable frequency with a slight gain between the two, so they don't interfere when the up signal doesn't interfere with the down signal. And basically from that, we can get extremely high accuracy with our navigation for, like I was saying, in terms of position, we can do accuracy within sub-meters of position. And in terms of velocity, we can do sub-millimeters in terms of velocity. And that's a spacecraft that's traveling, essentially at, 7.5, 8 kilometers a second. That's, 200 million kilometers away. It's incredible accuracy using nothing but, radio waves. For a mission like Perseverance, because the way that the trajectory works is we actually, when the spacecraft leaves, we actually go out of plane with the Earth and Mars. So we go up above the ecliptic and then we dive back down when we hit Mars. So we use a technique called delta door, which is delta differential one-way ranging, and that's how we're able to take out the out-of-plane errors from the injection. So the way we do this, we use the Deep Space Network. It's an extremely reliable system. We've been using it since the days of Apollo. It's an array of radio dishes that were designed and are operated by JPL on behalf of NASA. We have 3 complexes around the world. One's in Goldstone, California, the other's in Madrid, Spain, and the third one is down in Canberra, Australia. We use them for pretty much everything. That's how we get our data. That's how we send commands to our spacecraft. That's how we navigate. We can always use them for radio science and gravitation and grounding wave experiments. When I worked on Cassini, that was actually one of the experiments Cassini did while it was cruising out to Saturn was it did gravitational wave experiments. So a lot of uses. Pretty much these ground assets are the real stars of interplanetary spaceflight, because without this, we pretty much couldn't do our jobs. So now let's go to the fun part. So what Perseverance is going to be doing on Thursday? It's crazy to think it's just in a couple days. So EDL is the shortest overall mission phase, and it is also the most technically challenging part of the mission. This is there are folks on the team who will work for a decade for something that takes all of 7 minutes to execute. It's a very, very, very difficult concept. In spaceflight terms, we call this a critical activity. So the activity, which is land, must complete successfully or the mission is over. We crash, mission over, we've pretty much lost that first leg of the Mars sample return mission. So as a fall protection engineer, these kinds of activities receive lots of extra scrutiny. And we really, really, really think about how we drive these kinds of events to completion through a fault. So for example, let's say something we always look at with these events is, what if we get a computer reset in the middle of trying to do this event? Well, you obviously can't have your computer reset when you're trying to land, and there's all these very critical events that have to occur one right after the other to get to the ground. So what we do is we basically, we look at swapping to a redundant computer. We would look at holding that reset. So we basically would not let the computer reset until it gets down to the ground. Basically look at all the ways of how we drive that activity to completion through a fault. Even so far as letting a redundant system go down to get to the ground, because I'd much rather survive the rest of the mission with only one string than to let the whole spacecraft crash because I was trying to protect a redundant system. To add to the complexity of all this, we do this completely autonomously because of the one-way light time delay. And on the spacecraft, there is a sequence on board that they just, I believe, sent up over the week. I think they actually sent up yesterday. It's a sequence called do_EDL. It essentially is all the set of commands that we need in order to execute EDL autonomously on board the spacecraft. So I'm a systems engineer. I like looking at ConOps. So this is a very useful diagram for me to understand what is really going on here. So approximately 10 minutes prior to entry, we separate that crew stage, that spacecraft that's basically kept us alive all the way out to Mars. We don't need that anymore. We basically get rid of it. The spacecraft the rover has batteries, and that's what will power the spacecraft all the way to the ground. That crew stage will burn up in Mars's atmosphere. So we just get rid of it. We don't need it anymore. Atmospheric entry, what we call the entry interface point, is when we begin to first feel the effects of the upper atmosphere, and that's when the drag begins to build up and slows us down. We hit a peak heating at approximately 80 seconds. So this is where the outside temperatures are going to get as high as 1300 centigrade from that just hypersonic reentry, that plasma environment. We get our peak deceleration approximately 90 seconds after entry interface. And then once we finish with that, we're going to go into a guided entry. And we have a special technique that we'll talk about in the next slide that will then trigger the parachute to pop open. This is a supersonic parachute because of the way that Mars' atmosphere works and the velocity that we're going at. This parachute actually opens supersonically. Afterwards, we have to get rid of the heat shield. We don't need it anymore, and we actually need to get rid of it so we can see down to the ground. And being able to see down to the ground is what the radars and the cameras use in order to determine where the rover is and how to figure out where is a safe place to land and where is not a safe place to land. We'll talk about that technology here in a second. After we get close enough to the ground, we basically jettison ourselves from the back shell and we fire up our rockets. We divert away from the back shell. We go on powered, we go on powered rockets down to the ground. Once we get about 68, 40, so let's say about 20 to 30 meters above the ground, we're going to begin the sky crane maneuver. So we're going to take the rover and we're going to lower it down on a set of cables about 10 meters below the descent stage. We're going to continue that descent until the rover touches the ground. We wait a few seconds to make sure that we actually do in fact have weight on wheels. Rover fires a set of pyros. Those pyros cut the umbilicals. The descent stage flies away and crashes some safe distance away from the rover. And that's it. All done autonomously. This is something we call the 7 minutes of terror for a reason. If you remember from the Perseverance, or not the Perseverance, from the Curiosity landing in 2012, this is what we call the 7 minutes of terror. And this is going to happen again. It's going to be hair raising, and because of the one-way light time distance, by the time we get the first indications that the spacecraft has touched the top of the atmosphere, it's already been on the ground for 4 minutes. So one of the new enabling technologies we have for EDL is called range trigger. So what range trigger does is it reduces the size of our landing ellipse, which is our landing dispersion. So if you do a Monte Carlo assessment of all the dispersions, all the errors that can affect where you land, you get this air ellipse, what we call the landing ellipse. Range trigger is a technique that we can use that actually can shrink the size of that landing ellipse to about 50% the size of what it normally would be. So if you look on this diagram here, the blue is the proposed landing ellipse. So that's roughly 25 by 20 kilometers in size. With the range trigger ellipse, we can cut that down to approximately 10 kilometers in diameter. So much, much, much smaller. And that X there is the site where we want to go. So we divert slightly away from where we want to go because that terrain is really a place we can't land safely because of the slopes. But with range triggering, we're able to get much, much closer to the place that we want to go. So we don't have to waste months of driving to the location we want to get because of errors in our landing ellipse. So the second technology that we use, and this is all brand new, is called terrain relative navigation. This is actually a technique. This is actually a system that we're going to be using for the human landing system for crewed missions on Artemis. Is we're going to actually use TRN on the moon to do very precise lunar landings. So what the concept basically is we have basically a computer on board, and we have a set of cameras, and those cameras are looking down towards the surface of Mars, and they're comparing the images that the rover is taking to a database of images stored on board the computer that were taken from the orbiters previously. So we have orbiters that have basically been operating continuously around Mars for over 20 years. So we have lots of really high resolution images of Jezreel Crater. So the rover takes images with this actually it's called the landing vision system. It takes its images and it compares those images to the images it has on board that were taken from the orbiters. And the vision compute element, so it's all this separate computer that's doing all this processing because there's a lot going on there. We want the rover's computers to be taking care of actually, running the rest of EDL. So we kind of separate the two so that we separate the processing power from. But the vision compute element is taking those images, comparing it to them, and what it does is it creates a solution to say where are good places to land and where are not good places to land. And after the TRN completes its computations, it basically sends that information to EDL. It sends that information to the excuse me, to what we call the rover compute element. And that then determines where the descent stage, that rocket backpack, is going to land the vehicle based on that information. So let's listen to the team that actually developed the concept because it's really, really, really neat. And the way that they tested this is actually really interesting.
We are in Death Valley testing terrain relative navigation, the new technology for Mars 2020. The terrain in Death Valley is very much like Mars. It has a lot of sand dunes and steep slopes. It's quite similar to the landing site that Mars 2020 will be going to. We're taking a copy of the system that will be on the spacecraft, and we're testing it in the way that it would be used during the flight mission.
Terrain relative navigation gives the vehicle the ability to figure out where it is. This is kind of along the same lines of what the Apollo astronauts did with people in the loop back in the day. Those guys were looking out the window and looking for different craters and other features on the moon that they knew of from the maps we had on the moon. So that way they could figure out where they are and figure out where they needed to land to be safe. So for the first time here on Mars, we're automating that.
What terrain relative navigation gives you is the ability to avoid hazards that you already know about. So large hazards, hills, craters, things that you've seen before. With the camera, we take images as we're descending, and we match pieces of the image to orbital imagery that we have stored on board. And if we make many of these matches, we're able to figure out where we are relative to the map.
If we didn't have terrain relative navigation, the probability of landing safely at Jezreel Crater is about 80 to 85%. But with Mars 2020, we can actually bring that probability of success of landing safely at Jezreel Crater all the way up to 99% safe every single time.
We don't have an astronaut that we can put on board Mars 2020, but we can put this system, this terrain relative navigation system, so that the spacecraft can figure it out on its own.
I could see it being used on lunar missions, science missions, as well as human missions. Future Mars missions, of course, Mars sample return, Europa lander, landing on a comet, pretty much everywhere you want to land, you're going to want to have terrain relative navigation.
In order to test out that system, they actually hired a set of Hollywood stunt pilots for helicopters, and that's they basically told them, here's the flight profile we want you to fly. And they basically would take the helicopter, they'd pitch it down as if they were descending. They take the images real quickly and then they pull back up, and then they'd reset and go and do this over and over and over again to really test out the system, make sure it was robust, make sure that it could basically identify all of the pieces of all of the hazards in the area so that it could identify a solution of where it should land. So like they were saying, 99% probability of a safe landing anywhere in Jezreel, and that bump is what gave the science teams that were figuring out where to land the rover the confidence that they could land safely in Jezreel Crater, which is why they selected it over other landing sites. So now let's get to the fun part. So everyone remembers the 7 minutes of terror from Curiosity. This is the same 7 minutes of terror. So I will let the EDL team who designed all of this speak for themselves. This is a really neat video. It really gets the blood pressure pumping. It's gonna be a lot of fun regardless of what happens. Let's take a look here.
Nothing can be taken for granted when you get to Mars. There's a lot of things we just don't know.
Space always has a way of throwing us curveballs and surprising us.
I mean, until we get the data that says we're on the ground safely, I'm going to be worried that we're not going to make it.
Entry, descent, and landing is often referred to as the 7 minutes of terror because it takes about 7 minutes to get from the top of the atmosphere of Mars to the ground safely.
The spacecraft has to do all of this by itself.
There are many things that have to go right to get Perseverance onto the ground safely.
There's a lot counting on this. This is the first leg of our sample return relay race. There's a lot of work on the line.
Starting about 10 minutes before atmospheric entry, we get rid of really the spacecraft part of the rover that's been supporting us.
We come screaming in to the Martian atmosphere at 12 to 13,000 miles per hour.
And the heat shield is what dissipates all that initial energy through friction.
The vehicle will continue actually flying itself through the atmosphere. It's sort of like a transforming vehicle that went from spacecraft, and now it's kind of like an aircraft actively guiding itself.
When we're going slow enough, we deploy a parachute.
The biggest supersonic parachute we've ever sent to another planet. It's critical for slowing down the vehicle.
Perseverance's entry, descent, and landing borrows heavily from that of Curiosity.
But fundamentally, Perseverance is a different rover. She's bigger, she has different instruments.
We've added a lot of smarts on the inside to make it more capable so that it can deal with the landing site that we've given it.
The science team identified Jezreel Crater as basically an ancient lake bed and one of the most promising places to look for evidence of ancient microbial life and to collect samples for future return to Earth. The problem is it's a much more hazardous place to land.
You look at Jezreel, all you see is danger. How do we go to a site that we never thought was safe enough to go to before? So the heat shield, which has protected us all the way through entry, is no longer necessary. We need to get that off so that we can actually see the ground. And we can see the ground in a couple different ways.
Perseverance will be the first mission to use terrain relative navigation. So while it's descending on the parachute, it will actually be taking images of the surface of Mars and determining where to go based on what it sees. This is finally like landing with your eyes open. Having this new technology really allows Perseverance to land in much more challenging terrain than Curiosity or any previous Mars mission could. Amongst the rocks and the craters and the cliffs, these things are hazardous to the rover, but these are the things that are interesting to the scientists.
Once Perseverance has figured out where she is, we jettison the back shell and parachute and light up our rockets. Those rockets help us steer to a safe landing spot that's nearby.
That descent stage takes us all the way down to about 20 meters off the ground.
That's when we start the sky crane maneuver. And once the rover has hit the ground, the descent stage will cut loose from the rover and fly away to a safe distance. Surviving that 7 minutes is really just the beginning for Perseverance. its job, right, being the first leg of sample return, to go look for those signs of past life on Mars. All that can't start until we get Perseverance safely to the ground. And then that's when the real mission begins.
Okay. So yeah, it's going to be a really exciting day. And Ken, what I was wanting to do was to showcase a, so I don't think we have enough time here, but I will say if you go to mars.nasa.gov website, they have a real-time interactive landing simulation that will let you play through the entire EDL sequence from cruise stage separation all the way to landing. So we don't have enough time here, but I encourage you to go and visit the site and really check this out. It's really interesting. It'll give you a lot more information about how the EDL system works and all the little intricate little details that go into it. We just can't really explain all the little things that go into how it's working. Definitely check it out. It's really, really, really neat.
Mike, is it possible you can copy the link and paste it into chat room so people can see it?
I will do that. Okay, so let's set a few expectations for what's going to happen on landing day. So landing on Mars is really, really, really difficult. Statistically, only about 2 in every 5 missions are successful. It's about a 40% success rate, even for NASA. So Perseverance is NASA's 5th landing attempt for a rover. We are, knock on wood, 4 for 4 with our rovers. But landing is very difficult. There's no guarantees. It's because it's autonomous. There's just a lot of things there's a million things that have to go right, and only one thing can go wrong for the whole thing to not work. So for the key times, we expect entry interface here on the East Coast at about 3:48 Eastern time. Parachute deployment 4 minutes later at 3:52, and then touchdown at 3:55. So out there on the West Coast, just before 1 o'clock as expected signal. Now, the rover does have X-band system on board that will be sending back tones that the EDL team will be using to know when certain events are happening. We will also be relaying information through UHF link up to the orbiters. So they will try to hold lock with the vehicle all the way to the ground. There's no guarantee that we will have signal from the vehicle all the way to the ground. However, all of that data will be played back later with a relay and sent back to Earth. So we should have all of the information on the ground probably sometime later in the evening, once the teams have had a chance to just analyze it and look and see how it goes. Now, the reason EDL is going to be really neat for this mission is there are a set of, I believe it's 8 engineering cameras that are dedicated solely for EDL. So we're going to have 3 cameras looking up towards the parachute so we can actually see the parachute inflation for the first time. We're going to have a camera looking up from the descent stage to the back shell when we detach. We're going to have a camera looking down from the rover to the surface, a camera from the rover looking up towards the sky crane, and a camera looking down from the sky crane towards the rover. So for the first time, we're actually going to be able to see the landing occur. We're going to have actual video of it because all we have is telemetry to tell us how it went. We've never actually seen it with video. So I think that's going to really be a really great PR event for NASA. It's going to look incredible once all the video is processed and we can actually see it. So what comes next? So after Perseverance lands safely, which it's going to land safely, the teams will go through a systems checkout phase. So they'll do some checkouts and all the systems post EDL to make sure nothing got damaged on the way in. They will release the big constraint, the launch constraints. So for the mast, we'll release the launch constraint for the mast. We'll raise the mast cam up so we can finally get those cameras and the mast up and exposed. We'll release the HGA so we can do those high gain communications direct with Earth. We'll We'll drop the cover for Ingenuity. We'll lower Ingenuity down on the surface. We'll back away, and then they will do their test flights. And then we begin the science campaign, which is the reason we came to Mars, is to do the science campaign to assess the habitability of Jezreel Crater and to take core samples for eventual return to Earth using this guy. So the Mars sample return is now under study by both NASA and the European Space Agency. This is a notional concept for two elements of the Mars sample return mission. The one, that little rover that's closest to us, that is the proposed, what we call the sample fetch rover. That is being developed by the European Space Agency based on its ExoMars rover that we had hoped was going to launch in the same Mars window, because this was, the ExoMars rover was meant to be a technology demonstration for ESA that they could do surface operations. So we'll get some on the next launch window in 2022. We were really hoping we were going to get to see that happen in this window. But that's what we call the sample fetch rover. That is that goes with the element there in the back, that larger sort of lander looking concept. That's what we call the sample retriever lander. That is an element under study by JPL and will be funded and will be developed by JPL. The sample fetch rover sits on the deck of the sample retriever lander. It's deployed. The sample fetch rover goes out, grabs the samples, brings it back to the lander. The lander loads those samples into a capsule that we put inside of a Mars ascent vehicle that is also on the platform. And then autonomously, when you'll see there, bullet number 4, the Earth Return Orbiter, which is being developed by the Europeans, when it is in the correct alignment, we will autonomously, for the first time, launch a rocket from the surface of Mars to perform an autonomous rendezvous in orbit to transfer those samples to the Earth Return Orbiter. The Earth Return Orbiter will leave Mars orbit, and it will eventually, and it will return to Earth. It will put the samples inside of a capsule that will re-enter Earth's atmosphere, and we will have the first direct samples of Mars here on Earth to study. There's a lot of elements that have to go to make that work. It's very challenging. Right now, the proposed launch window opens in July of 2026, with samples returned no earlier than 2031. It is under study, but it is not funded yet. So, eventually we will go get those samples. It's just a case of when we will go get the samples is another story. So for your resources, you can basically go to this link, mars.nasa.gov /Mars 2020. It has all the information that I've presented here, all the videos, the press kits, that EDL landing demonstration that I was showing, as well as mission updates. Once the rover is on the surface safely and off doing its science, and everyone forgets about Perseverance because it's just doing its science, and it's not the really fun, interesting EDL portion of it. I think, Ken, that is all I've got. So how about I stop sharing?
Okay, yeah.
Chat here.
For the Q&A box, if we have a few minutes, we can do 5 to 10 minutes if you have time.
Okay. Yep. So Veronica is asking, how long will Percy take to send home the data? Is 9 minutes and 21 seconds accurate? I believe on ED, I believe the latest information from the team is that it's going to be about 11 minutes and 21 seconds is the one-way light time delay. So in terms of sending the tones back to Earth that are telling us what the how EDL is progressing, that will be done in real time with an 11-minute and 21-second light time delay. Now, the core amount of the data that we take during EDL, that will be sent up later on a relay through the Mars Relay Network, and we should get that probably sometime later in the evening on the 18th. If not on the 18th, we probably will have it at least by the next day. So just kind of have to be patient. All that information will be available on the Mars 2020 website. So, okay, D. Hansen is asking, in my opinion, what can be applied to Gateway for the Mars mission? So as we were talking about that terrain relative navigation, that is a technique that we really want to use for doing accurate accurate landings for Lunar Gateway, for the HLS system for crews, as well as doing precise landings for those commercial lunar payload services. TRN has really been in development for quite a while, for at least a decade. It's been under study, but we're finally to a point where the technology is good enough that we can actually put it on an actual mission. And I know that the Mars 2020 folks really fought to get TRN on, because that's what enabled the scientists to be able to go to Jezreel Crater. Because we said only 80% without TRN, it is just too risky with a mission of this, with a mission that's trying to do actual astrobiology experiments. We want to make sure that we can actually get the information back from the rover. We want to cache samples. So getting TRN on the EDL system is what enabled us to go to Jezreel Crater, and that's where the really cool science is. So, fingers crossed. Engineers, we don't believe in superstition, but we really want to see EDL work well next week. And TRN is going to be a technology that's going to make that happen. Okay. So Rich Lehman, I hope I didn't butcher that, asking for the link to the Mars landing website. I will post that in the chat before I head out, so everyone can go check it out. Let's see here. Veronica is asking, what did you consider in order to be enough sure that the samples will not be hit by storms after they've been deposited? Yeah, so we're talking about dust storms here. So the tubes are hermetically sealed. So once they're on the surface, there is no way that the samples can then be contaminated from Mars's atmosphere. Now, because we're talking about dust storms, the dust storm is what killed the Opportunity rover. Because of this planet encircling, we call it a planet encircling dust event that deposited dust on its solar panels and basically made the rover was not able to survive through that dust storm to charge its batteries. But because of the pressure at the surface of Mars is only 1% of that on Earth, once the samples are deposited, they're not going to roll away. They're not going to. We know they're going to stay where they are, because even a 60 to 70 mile per hour gust on Mars it wouldn't even feel like a light breeze, because the pressure is just so low. So we know once the samples are deposited, they're going to stay where they are, and we'll go out and eventually pick them up for return. All right, so Mike is asking, are there any ideas to purposely contaminate Mars? No. When we're still trying to answer that big question of, was there life once on Mars? Until we're able to kind of answer that question, we don't want to forward contaminate Mars. So we take our planetary protection very seriously. When you're in the clean room, folks are fully smocked, so they've got their shoes in smocks, they've got their hair covered, they've got glasses on, they've got face masks. We make sure that we clean the surfaces. The rover is exceptionally clean before it leaves Mars, and that's so that when we try to answer that question of, we bring a sample back to Earth from Mars, is that bacteria that's in that sample, was that there to begin with, or did we take it with us? We're very, very, very particular about making sure that we don't take our germs with us. Okay, so Ken is asking, when or at what stage the helicopter will release, and how long could they operate? So the helicopter will be released likely within a few days of landing on the surface. They have to do the systems checkout first. They got to get all the data off from EDL and make sure everything is working fine. And then they will release the dust cover on the bottom. They'll deposit the rover. They'll back up from it, and they'll probably go off and do their flight tests. And then at that point, the rover will then basically just go off and leave the helicopter where it is, so it can go off and do its mission. Ken also asks, hey, Ken, was this question for, you're asking about Starship SpaceX stuff. Was that for me, or was that for the previous?
But because you mentioned that in the next 100 years, there probably no upper stage can approach Mars, but now Elon Musk are seriously building the Starship.
So
what is their vehicle there when they approach
Mars? I don't know the so that's kind of a little outside of my area of expertise. I will say that as long as SpaceX intends to launch their rockets from within the borders of the United States, they still fall under the FAA, and planetary protection in particular is going to be very important. I mean, as long as they're not landing in the places that NASA is trying to study, I don't think there's a problem, and I don't think there's much we can do about it. But NASA definitely will, I would expect that they will have a say in where starships are allowed to land, simply because we're still trying to conduct those scientific studies. So Rich is asking about, does this mission have a Marco CubeSat range in common? No. They, a neat story about Marco. Marco was designed with InSight because in the original launch window of 2016, the way that the Mars Relay Network was phased at the time, there wouldn't be an orbiter overhead. The rover or the spacecraft went in to do its EDL. So in order to have that real-time link back to Earth, JPL created these two CubeSats called Marco that would fly along with InSight that could provide real-time EDL information as the spacecraft went into Mars. But when we got to 2018, that phasing issue wasn't a problem anymore. So long story short, Marco was created to fill a gap in being able to see real-time EDL telemetry for InSight. Perseverance does not have that problem. We have sufficient orbiter coverage as well as sufficient X-band coverage for direct to Earth that we will be able to see. We should be able to see EDL all the way to the ground. Veronica is asking, are the cameras used for the TRN on the rover? Do they start to work only when the heat shield is attached? So those cameras, what we call the lander vision system, those cameras are turned on autonomously by the computers on board. They can't really start taking images until the heat shield is deployed. Now, I'm not actually sure how the sequencing works, but once the heat shield is away, they will start taking their images. And within, I think I've seen within 30 to 45 seconds, they will have a TRN solution that will then be sent to the rover computer that will then direct the descent stage of where is a good place to land and where is a not good place to land. So Mike is asking, am I going to watch the landing? Actually, yes, I will be doing a live stream for the Kansas Cosmic Fair and Space Center during the landing. I will try my very best to stay very composed during it. EDLs can definitely be very stressful times. And because this is a mission I actually worked on for a little bit, I have a little bit of a vested interest in it working correctly. So I will definitely do my best to try and stay calm, but my blood pressure will probably be a little elevated until I get down to ground safely. Okay, Randall is asking, is the telecom system operational during dust storms? Yes, it works just fine. The wavelengths for UHF and X-band are small enough that they can penetrate right through dust storm particles, even the largest dust storm particles. So that shouldn't be a problem. And we're actually landing in not dust storm season. It's actually not dust storm season right now on Mars. So yeah, we don't have to deal with those problems, and we don't have to deal with the same problems like what InSight dealt with. Is they landed following a major dust storm on Mars, so they actually were able to. I believe they were able to actually pick up when they were hitting dust with the heat shield because there was still lots of dust left in the upper atmosphere. So Randall's asking, what test would be definitive proof of life in a Mars sample? The only way that we can actually definitively say that we have found ancient microbial life in a sample is to bring it back to Earth. The rover instruments are very, they're good in the sense of being able to assess the habitability and the potential to support life, but they are not to the level, they don't have the level of accuracy or the sophistication or the thresholds to really say whether or not that organic signature we saw in the instrument is actually an actual microbe. We have to get the samples back to Earth in order to make that final assessment. Even if they find something in the imaging that gets the scientists really, really, really going to think that they found something, we cannot say for certain until it gets back to Earth. Let's see here. Ken, I think I got them all. So I will post the web link in the chat for everyone to look at. Definitely go check it out. It's really neat. It didn't have that for the Perseverance landing, so you actually get to kind of see all the major techniques as they happen, and that simulation should be accurate within 1 or 2 seconds. There is a little bit of uncertainty in the exact timing because there's still uncertainties about Mars's atmosphere, but that timing should be accurate within a few seconds.
Yeah, thank you so much. Yeah, our time is up, so Dr. Crane is waiting. So yeah, really thank you so much. This is so exciting. Everybody was so heated up. It's just amazing. So
yeah, thanks for having me, Ken.
Yeah, stay in touch. We should come back again and to update, with our the progress, afterward.
Very good.
Stay in touch.
Yep. Bye-bye.
Bye-bye. Okay, so our next speaker, Dr. Crane.